Good morning to all. For those who have come from all parts of India to this classroom over here, students, faculty members, and people from the industry. And also I welcome everybody who is on the internet watching us live to this program on GIAN program on acoustics and industrial noise control. This is a program which will be running for a week from today till the 19th of May. We have faculty from Purdue University, Professor John Stuart Bolton, who is with us, and he will be taking a few lectures on this course. Well, before I begin into the details of these courses, I again welcome you on behalf of IIT Kharagpur, and I hope you all have a comfortable stay while on the campus, and you get to enjoy the hot summer months in Kharagpur. And coming to the course, acoustics is a wonderful branch of engineering science, as you may call it. It involves something to do with our human hearing. Okay, if you look at an energy point of view, God has made our ears so sensitive that even a tiny amount of energy which is incident on our eardrum gives us a sense of uncomfortable feeling. And this branch has thus evolved mostly for human comfort. So as designers, as engineers, we have to design machines, products, processes which produce less noise. So in this course, we will be going into the science of acoustics, how this noise is being generated, how does it propagate in the media, and then how we receive it, what are the ill effects when we receive it, if the levels are very high, what happens to our nervous system. We fall sick on an exposure to a prolonged for a prolonged time at higher levels, we lose our hearing. So, and considering all this, the governments throughout the world have made standards which limit the level of noise which has to be emitted by machines, the level of noise which should be there in our surroundings, in our residential neighborhoods, in our community, and so on. So in that sense, this is a very important field of engineering, where we study both the science behind it, that is the acoustics part, and then applying the science to design products, processes, and which produce less noise, and that is the industrial noise control aspects of this program. So, well, I am Professor Mohanty from IIT Kharagpur, and those of you who need to get in touch with me can contact me over email or through the IIT website. And those of you who are watching live can refer to me or contact me by email or through our website. So I once again welcome everybody to this program. Now coming to the course contents, of course, vibration produces noise. So we need to study the basics of vibration. And I always tell my students in the classroom, if you know 1 degree and 2 degree freedom system of vibrations, you can solve maybe 90% of the vibration problem in engineering. Okay. And so vibration itself is a 40-hour graduate level courses in many universities, but we will be discussing briefly about for an hour on the basics of vibration. And then we will be talking about the basics of acoustics, on the wave propagation, on the state space equation, and then the solutions to these wave equations both in 1 dimension and 3 dimension, what happens to this acoustic pressure. Because if you realize, acoustic pressure is a small perturbation of the pressure wave which is riding over the ambient atmospheric pressure. In fact, right now our eardrum is exposed to a atmospheric pressure, okay, and that's a very high level, 10 to the power 5 pascals. But when I speak, there is a small perturbation of this pressure wave front, which is propagating and get incident on your wave on your eardrum. So this even 1 Pascal of pressure fluctuation is loud enough to give us an uncomfortable sense of sound. Okay. And then these wave fronts of acoustic wave fronts, when they interact at the boundaries, many things happen depending on the impedances of the boundary. I mean, some will get absorbed, some will get reflected, some will get transmitted, and this forms the basis of the materials which are used on the boundary of an enclosure, of a material, etc., so that we can play with these wave fronts, so that the sound field or sound level inside an enclosure will appropriately reduce. And then of course, we have to mathematically model many of these sources, and as you all know, sound, human hearing, we hear somewhere from 20 hertz to 20 kilohertz, and then the speed of sound in air at room temperature is 343 meters per second. So, there is a wavelength associated with this propagation speed of sound, C by F. So, many acoustical phenomena will depend on this wavelength and sources. What is the dimension of the source compared to the wavelengths? So, we can treat some sources as simple sources and some are big sources, and what happens to that, and so on. When you have multiple sources, as good as having one loudspeaker, multiple loudspeakers, what happens to the sound field in that scenario? One machinery vis-a-vis many machineries in a shop floor, what happens to the noise field is something we will understand from studying about acoustical sources. So, just to briefly tell you, so this vibroacoustic is nothing but study of the transfer of an energy from a source to a receiver, and receiver being the human being. So, this transfer of energy depends on the type of wave motion which is happening in the medium, and this medium could be solid, medium could be a fluid, and depending on the medium, the type of wave propagation is different. If you all recall your high school physics, some are longitudinal waves, some are flexural waves and transverse waves. So, we will see how this wave phenomena helps in propagating the energy from a source to a receiver. Okay. And then in noise control, there is a lot of this wave front. Now, we need to understand its frequency content. Okay. So, to understand the frequency content of the acoustic wave which is being incident on us, we need to process those acoustic waves as signals. So, we will be talking about little basics of signal processing, okay. And then again if you recall from your high school physics, a wave, some amplitude, if this is the time period, the frequency of this wave is nothing but 1 by time period. But acoustics waves, when we measure, and you will see they are not so nice pure tones. If I put a microphone even, and I am sure all of you must have seen an oscilloscope, they look something like this. So, the question is, what is the frequency content of such waves? Okay. And that is where we will be getting introduced to signal processing, because all these materials, etc., which we will talk for noise control, they are behaving differently at different frequencies. So, I need to characterize my source in terms of the frequency content, and that is why the signal from the source or the noise from the source has to be processed, and that is what we will study about in signal processing. And then methods like fast Fourier transform, how they are done to understand the signals, talk about filtering, what are octave filters, 1/3 octave filters, and so on. Then of course, to measure any signal, I need some measurements to be done, some instrumentations to be done. All of us use microphones to measure a sound signal. So, what are the different types of microphones available? Is it only the sound pressure level we need to measure, or there are something else like sound intensity level and so on? So, what are the different types of instrumentation available? Sometimes it so happens that my machinery is somewhere deep in a mine. Obviously, I cannot be sitting down in a mine and doing my signal analysis. It is not comfortable or not convenient. So, sometimes we need to record these signals in a medium. It could be a digital audio tape. Of course, nowadays we have the DVDs and digital recording and so on. So, we need to understand how these recordings are to be done, what kind of frequencies we need to record these signals at, so that we do not lose any information being carried by this signal. And then we will see what are the other instrumentations in terms of vibration measurements. And related to this, we will be also taking you to our laboratories. And of course, those of you who have joined us at IIT Kharagpur are lucky enough to visit our laboratories in the afternoons to see all the different aspects of measurements. And again, those of you who are outside can access our our lab through a link which I will give at my website, and so that you can see the facilities and so on. Then now so this would be the basics of acoustics, signal processing and measurement. And then towards the later half of the course, we will be talking about different aspects of noise control. Again, if I was to define what is the difference between sound and noise. Sound is any acoustic wave which is generated and which we hear, but noise, as it is known, is something which you do not like. Okay, so music to somebody's ears could be noise to somebody else. For example, a youngster would like a rock music, but parents would say that's noise for us. Okay, so that's, and of course anything which you do not like is noise, and that is where we as the noise control engineers need to fix it so that people are comfortable and do not complain about the levels of noise. And then another aspect which is taught in noise control is this: what happens to the propagation of sound waves in a one-dimensional duct, okay, and how does it behave, and if this duct is terminated by a certain system which has an impedance. So if there is an acoustic wave front going, and if I terminate this by some impedance, we are going to discuss about this. So the reflected wave would depend on this termination impedance. So this is a one-dimensional duct. So when you talk about HVAC systems, sound waves, traveling in an air conditioning duct, sound wave in an exhaust pipe of an engine. So depending on this termination impedance, because I do not want anything to come out at this end, and I want a very low noise here. So I have to play around with this. Okay, either termination, or I can have some elements here which will reduce this transmitted wave. Okay, it has to be very, very low, and that is what we will study in mufflers. That these are known as the reactive mufflers, but then I can also put certain materials, okay, and this will become dissipative mufflers. Because this, depending on the material property, the sound waves could get absorbed, and then I would not have anything coming out of the tailpipe of an automobile. So you would have seen in every car we have a muffler or a silencer. So the end effect is I want nothing to come out at the exit. So a designer has to do a good job on the dissipative part, or having certain baffles and perforates so that we reflect it back to the source. Okay, and that is what mostly we will be talking about in ducts and mufflers. Of course, there is another type of mufflers wherein because essentially when there is an obstruction to flow, there is a back pressure buildup, and this back pressure is going to affect your engine's power output. So there is a compromise which we have to do so that I do not compromise on the back pressure and the power output of the engine. So that's a safeguard. As designers, we have to be careful about that we do not reduce that. And then another very important aspect is sound quality. Human beings perceive sound differently, and let me tell you this: our human ear, God has made our ear if I had put a microphone, it would have measured whatever is the output to input could have been 1. Okay, that is what a microphone would have measured. Okay, but human ears, what we perceive is something different. We hear it this way. We hear poor at low frequencies, and God has made our ears like this. So, our ear is highly nonlinear. Okay. So, we perceive sound differently than what a microphone would have measured, microphone being a linear instrument. So, there are many metrics which relate well to human hearing for a particular type of noise. Noise, for example, you will see noise of the same level. With some noise we enjoy it, some we do not enjoy it. I will give you an example. I mean, imagine you are in a guest house. It happens in our guest houses in India. Okay, you are having a nice comfortable sleep in your room, but there is a leaking faucet in the bathroom and the water is dropping, tap, tap, tap. The noise level could be low, but this irritating dropping noise of the water drops is irritating to you in the middle of the night. Okay, that is how human beings perceive. That is one example I thought I would give it to in the class. So, perception of sound is a field of engineering where designers themselves are taking care right in the design stage that what is the critical dimensions, and then how does it affect the sound quality. Is it being appreciated by a group of people, which is the jury evaluation of the sound produced by that component which you have designed. Of course, today the state of the art is we need not even build a prototype. The computer aided engineering techniques are so advanced, without even manufacturing a vehicle we can hear how the car would sound once it is manufactured, the interior acoustics, the exterior acoustics. So, you can imagine what kind of lead time we have through CAE. And I remember 25 years ago when I was at Ford working on designing cabs, we used to have prototypes where we used to manufacture and measure. Okay, but then today state of the art is you need not go spend money in manufacturing. You might as well do all CAE simulations and hear the noise and then see you like it, you do not like it, change the parameters, and that is the state of the art today in designing products which appeal to your sound quality and so on. So, and then another aspects of sound quality, which is listening to the sound of a machinery, you can also get a clue as to what is wrong with it. And then we have an expert on sound quality who is going to speak on how machineries fault could be identified by listening to this sound. Okay. Of course, another very important related aspect is human hearing, and that is why we all are here. Okay. We want noise levels to be low so that human beings do not suffer. And if you have been to many of the shop floors, of course, now because of the regulations, be it the ISO standards, the OSHA standards, there are regulations from the regulatory body as to what is the maximum level of sound where a person or a worker needs to be exposed to. What are the limits? Even in India, our Central Pollution Control Board has set norms as to what should be the noise levels produced by vehicles going on a highway, and then what should be limit of that is known as the pass by noise. We have it for motor vehicles, and in fact any motor vehicle manufacturer who sells vehicles in our country or exports to other countries, they have to adhere to their local pass by noise level limits. And of course, India we have a festival of Diwali, okay, where we burst firecrackers, and if you will recall, when we were kids, we used to enjoy bursting crackers, but now there are regulatory requirements as to when a manufacturer cannot sell a firecracker if it does not meet the pollution control board norms as to at certain such distance. We will discuss that in details. What should be the maximum noise level of that firecracker? Otherwise, you cannot. And of course, the government has also regulated in terms of public loudspeakers. At 10 o'clock you need to shut down, 6 o'clock is 10 to 6, nothing should be playing. Okay. So, there are issues on that we will discuss. And then of course, India government is right now working on the airport noise, and we are doing something at IIT Kharagpur on the railroad noise, okay, and how the cabin crew in a railway or locomotive are comfortable. We will see in a case study what kind of levels they are exposed to, and then what are the measures which are being put to reduce the noise levels in the cab of a locomotive, so that the poor drivers who drive 8 hours without any break are at a comfortable hearing level. Okay. Now, having done the basics, then we will now slowly move into the principles of noise and vibration control. And noise control cannot be done in isolation, because a vibration of a body, if it is a body is vibrating, the air molecules next to it would vibrate, and that would be the acoustic waves which would be vibrating. Suppose this is my machine surface, for some reason there are some forces, and then this surface is vibrating. So, if you look at the air molecules very close to it, they would vibrate, and then there will be a local reduction and increase in the density, and then this is how this wave front is going to propagate. So, vibration will induce sound field, and so we need to understand how this vibration could be reduced. There is a techniques of vibration isolation, techniques of reducing this vibration radiation efficiency. So, we will talk about these principles, and then if you look at the principles of noise control, I have a source, then I have a path and a receiver. So, this path could be structure borne and airborne, and airborne paths how we apply certain materials to control them, and structure borne how to reduce the vibration energy is which we will cover. Then we will talk about a particular case study on automobile noise control. What has happened to the auto industries throughout the world because of global competitiveness? All of them of course meet the regulatory pass by noise levels, but people are working on interior noise levels. If brand A is quieter than brand B, the manufacturers are looking into technologies wherein they can reduce the interior noise levels. And sound is a very important aspect. You will see if I have 2 components or 3 components, A, B, C, and this is some level, say x A, x B, x C. So, you will see later on in acoustics, if these were 3 machines which needed to be, the overall noise needed to be reduced, it would be appropriate to first reduce the level of x B because of this logarithmic additions. So, as a noise control engineer, I need to rank the noise source in terms of their level and their frequency. So, one with the highest level needs to be reduced first, then subsequently the others would be reduced to reduce an overall level. Okay, somebody says, I spent a lot of money and made XC very less. It would not work because your XB sticks out. So, one has to be very careful about it. And this is interestingly what has happened in automobiles. As we work with auto companies, I see earlier they were more interested in reducing the engine noise which comes in through the firewall. Okay. But once that was taken care of, people are worried, then we are worried about the tire noise coming in through the door sills. And now people are talking about little knobs or the HVAC units or the car seats making a squeaking noise. So, these are the problems because they have reduced XB, now they are worried about XC, XC and so on. So, that is the funny part about noise control in automobiles. Okay. Of course, and of course, there are other issues on noise control which we will be discussing. Then another work which we have done actually at IIT Kharagpur on this use of natural materials. Globally, people are working on noise control using natural materials, and then we have characterized natural fibrous material jute, which is widely available in Bangladesh and India, and we have studied their acoustical properties, and we have applied them for noise control in some home appliances. So we have an expert in that area who is going to talk on these noise control aspects using jute or the natural materials. Of course, there are a few other issues of noise control, particularly building acoustics, architectural acoustics. How do you design an auditorium, a classroom, a place of worship? There are parameters like reverberation time. How is the absorption in a room controlling its reverberation time? What do you do to the walls so that you do not hear any outside noise coming in? How do you control the HVAC noise? What is the noise field like? Suppose people should be able to understand one's speech. What is the speech interference level? So these are issues in building acoustics which we will be discussing about. And then another very important aspect of noise control is this active noise control. The problem with passive noise control is, later on you will see, at low frequencies we require more amounts of material, okay, and that creates a problem because we may not have enough space to keep the materials. So active noise control is a good candidate, wherein through the electronics we produce a signal which is opposite in phase to the incident sound field, and we create a destructive interference, and then we reduce the sound pressure level. People also do active vibration control for engine mounts or vehicle mounts to reduce the vibration level, and I am sure you must have heard the popular active noise control headsets, etc., which we will get to see in the lab as well. And then there are a few other case studies which we will be discussing as the time goes towards the end of the week. And of course, we have Professor Bolton, who is going to share with us his views on the future trends in noise control in terms of metamaterials, acoustical holography, and so on. Well, those of you who are joined us in Kharagpur are lucky enough to visit our laboratories, wherein we will be showing you some of these experiments on basic sound pressure level measurements, sound intensity level measurements. How do you calculate the sound power of a machinery by measuring the sound intensity? How do you measure the reverberation time in a room, which is dependent on the absorption present in the room? And we will see some demonstrations of sound quality as to the same sound level. One you will like, one you may not like to hear at, because that's something. So it is always not SPL. There are some other metrics which you will see. At IIT Kharagpur, of course, we do a lot of projects for the Indian Navy on the underwater noise. So we will demonstrate how underwater noise is measured, and then we will introduce you to some filtering of signals through octave band filters, narrow band filters. And then another aspect is finding out the resonance of a vibrating system. Okay, so experimentally, how do you do a modal analysis to find out the experimental natural frequencies of different structures is what we will see. And then, like we have sound quality, people nowadays are also worried about the exposure of human beings to high levels of vibration. If you are holding a drilling machine, jackhammering, the worker is exposed, worker's fingers are exposed to high levels of vibration. If you are sitting in a car seat, you would not be comfortable if the car seat vibrated. Think of the earth moving machineries. Think of the operator exposed to high noise levels and high seat exposure levels of vibrations. So there are again ISO standards as to what is the maximum limit of vibrations which a worker or an operator needs to be exposed to, and you will see how those seat accelerometers or accelerometers put on fingers could be used to measure the exposure level of vibrations to a person. Of course, when you talk about vibrations, it is very easy to measure the linear vibrations x, y, z, but of course there is also rotational measurements of in every linear direction. There is also rotational vibrations of theta theta or theta dot or theta double dot. So we will see how using a rotational laser vibrometer, the rotational vibration of systems could be measured. And then I was mentioning to you regarding this data which needs to be measured at this site. So what are the principles behind data logging, and then we will show you how data recording is done for a given period of time at what sampling frequencies. Then of course, sometimes it may not be possible for us to go to a place and measure the vibrations. How from a distance using a laser beam we can measure the vibrations of a structure is what we will discuss about. Then in the laboratory we have an impedance tube setup, wherein we can measure the absorption coefficient, the transmission loss of different materials, and then which we will see how it is measured. Then of course, we will have a demonstration on active noise control using a headset. Well, if you can read this, you have this schedule in your handout. So now I will briefly come to some of the logistics part of this course. We are having a 4-hour lecture every morning, every day in fact, 2 in the morning and 2 in the afternoon, and then with coffee break, lunch break, and so on. Since we have a large number of participants at Kharagpur, we have in the laboratory sessions in the afternoons, I have divided that the first group on Tuesday afternoon, the participants from the industry and academia come and visit our lab, and then the students outside IIT Kharagpur come on Wednesday, and the IIT Kharagpur students come on Thursday to the lab. Of course, at the end of the course on Friday we have a quiz, and that is only for the students who want grades. Okay, if you do not want grades, that's fine. Okay, otherwise you get 1 credit grades, which could be transferred to your university as well. Okay. Now I will come to the guest faculty who has come all the way from Purdue University. I have with us Professor John Stuart Bolton, who is a professor at the Ray W. Herrick Labs of School of Mechanical Engineering at West Lafayette main campus in Purdue, and he will be taking about 12 lectures, and then he will be with us in the lab, and is available on the campus for any time you want to talk to him, discuss with him on Q&A and any issues you may have with him. Thank you, Professor Bolton, for taking all the pains to coming down to India and welcoming. And the first time he is coming to India, and I understand you are enjoying the Indian food. Okay. And he will be speaking to us today afternoon with the basics of acoustics. So what I will do now is, and then I have 2 other guest faculty. I will introduce the guest faculty first, and then I will ask each one of you to tell me briefly about yourself, where you come from, and what you expect out of this course, and so on. So the cameras will be going one after the other. Next is I have Dr. Shah Fatima. She is from IIT Delhi. She is going to speak on natural materials for noise control. Okay. And then Dr. Fatima should stand up. The camera would know that to zoom on you. And that's Dr. S. Fatima from IIT Delhi. Okay. Thank you. And I have another guest faculty, Dr. Sneha Singh. She is a PhD from Warwick University, and she is a postdoctoral fellow with our group, and she is an expert on sound quality. She is going to speak on sound quality, and Dr. Fatima and Dr. Sneha Singh are going to help us with the lab, along with a few of my students who are there in this class. Okay. I will now come to the participants. I would ask them maybe to stand up so that the camera guys know to zoom on you, and then you can tell us your name, where you come from, and what do you expect out of this course. I'll start with you.
Hi, I'm Shreya. Do I look here?
You can look here and there. Yeah.
So, okay. I'm Nishpriya. I come from Shivnada University in Delhi. And basically, I'm not from engineering. I'm doing PhD in sociology. But I'm interested in mapping sound in the industries of Surat and how scientifically and empirically you understand sound compared to social. So that's it.
Okay. Thank you.
Good morning, everyone. Myself, Ullas Marwade. I am from a JSPM group of institutes, Pune, and I am doing my research in natural materials. So I was following Mohanty sir and Fatima ma'am. So I am very lucky enough to have both of you here.
You have another expert, Dr.
Yes.
Bolt almost.
So that is also very interesting.
I am from JSPM Group of Institute, and I am a PG student. And currently, I am working on natural materials and my PG project. I came with my professor.
Can you just pause till the camera looks into you. Yeah, please go ahead.
Good morning, everyone. My name is Vivek Iyer, and I am from Charusat University, Gujarat. And I am here to get basic knowledge regarding acoustic and industrial noise control.
Hello sir, Manish Raj from IIT Delhi. I'm working in the field of voice.
Please.
Hello, good morning everybody. I am Suresh Srivastava. I am from IIT Kharagpur. And what my expectations from this courses are towards noise measurement, modal analysis, and of course isolation.
Good morning. I am Chinmaranjan Barik from IIT Kharagpur. Actually, I am working on breathing vibration. It's little bit different, but still that underwater vibration and that noise control also. I just want to know these things, so I'm trying to.
Morning all. I am Devasith Panda and I am from IIT Kharagpur and I am working on noise control, so that's what I expect.
Please.
Good morning everybody. My name is Vasaveshwar Rao. Basically I am from Indian Railways and now I am on deputation to Indonesia working for Jakarta Metro. So mainly I came for this program is to know more about vibration analysis, because in Delhi Metro Rail they were implemented mass spring system at different locations in Delhi Metro, but I was not much happy about it, because the way they were working, of course I didn't tell them anything, but I felt they were not doing the correct method, applying the correct methods. So I have asked one chief engineer, Mr. Mishra there in Delhi Metro, the noise levels and vibrations levels at old age homes or parliament building or hospitals or any other schools. So he tried to say something, but the method they were using, to me it was not up to mark. So now in Jakarta Metro we have some manuals, but I went through those manuals, but then I came to know about this GIAN program, so I have taken this opportunity to come and attend, so to clear my doubts in this program. So if possible, I will try to appraise the officials at Indonesian Railways, Director General Railways. So I will present all this, what I will be going through for 5 days. So I hope the vibration, because Jakarta, Indonesia is one of the largest Muslim country in the world and very peace-loving country. So the thing is that, but the metro system in Jakarta is constructed by Indian officials, and many are from IITs. IIT Kharagpur also is there. 2 of them couldn't manage to come here, so they told me to go.
Okay, thank you.
So I have come back. Okay. Thank you all. Very good.
Good morning to all. I'm Mahavijay. I'm working as a senior engineer for noise and vibration measurement in AG equipment, company manufacturing of screw compressors and buccal compressors. I'm managing my noise and vibration lab. We also have transmission labs, computer institute, and all the LMS system on that. This also will help me to improve my work. Thank you.
Okay, thank you.
Hello everyone, I am Karthikeyan. I am coming from TVS Motor Company. I work as a design engineer of induction and exhaust system. So basically my expectation out of this course is like our customers perceive sound quality as the attractive quality of the vehicle. So I want to learn more about that and incorporate the same in our designs, in design stage, and solve the problems much earlier stage.
Okay. The person next to Sneha, yeah, please.
Hello everyone, I am Prakash. I am from IIT Madras, final year undergraduate in civil engineering. So I will be pursuing my MS in Geotech in CISC, which is Infrastructure Systems Engineering. So I just wanted to have a look at industrial noise control and see how I could use it for later for my thesis.
Okay, good.
Good morning everyone. My name is Dulpan Vishnesh. I'm from DRS Solution. Actually I work as a sound engineer designing for auditorium and sound. So I come to know about Professor Mohanty and some of my project. So I am interested to know about acoustics and noise control so that I can sound interesting better in design.
Okay, thank you.
Hi everyone, my name is Mohanty. I'm from IT Kharagpur and I'm working on the design of a low-speed wind tunnel and an axial fan. So we are working on perforated screens to attenuate some of the noise and foam concrete linings. And I'm also working on the turbo machinery noise, basically the modal, the plate passing frequencies, its harmonics, rotational harmonics, and the broadband noise.
Good morning everyone. My name is Mohammad Mujahid Khan. I came all the way from Amiya Islamia. So in our lab we are working for we are computationally analyzing the interaction of the hydrodynamic and entropic modes with the acoustic mode when the fluid flows. So I am looking forward for the more knowledge about this field, that is the flow-induced vibrations or flow-induced acoustics.
Okay.
Good morning all. I am Anush Kumar. I am faculty at GIAN Course, and we are planning to set a vibration and acoustic lab. So please.
Hello everyone, I am Orphan Halder. I am from this institute. I am a mining graduate, and I joined this course to know the basics about this noise control and all.
I am Maxim Rahul Bharati from IIT Kharagpur, doing research scholar. My research area is underwater acoustics, students of GIAN Course.
Hello everyone, my name is Levin Nishan. I am from IIT Kharagpur and I am pursuing Master of City Planning in Architecture and Physical Planning, and I want to know how to use the noise in the building.
Good morning everyone. I am Krisha Pranas. I am second year medical student from IT Kharagpur. I have done my graduation in architecture, so I am more interested to learn how to engineer acoustic. That's what from my experience.
Good morning everyone. I am Vishwajit Sahu. I am a PhD student here at IIT Kharagpur and I work in the signal processing field basically, but my aim from this course is to know basics about acoustics and some measurement techniques.
Good morning everyone. My name is Akash Srivastava. I am a research scholar from IIT Kharagpur and I work on vibration based condition modeling.
Thank you all. There are few participants who are still on the train and some are late, so we'll be having few more in the rest of the week who will be joining us. I would now request Professor Bolton, you can sitting there and give some of your remarks and on this course. Okay.
Okay. Well, first of all, good morning. It's a pleasure to be here. I'm grateful for the invitation to attend and to participate in the short course. So my thanks to Professor Mohanty for organizing this. Maybe just a few words about my own background to begin with. So originally I'm from Toronto and did my undergrad degree at the University of Toronto in Canada, but then ended up going to Southampton University in the UK to do a master's and PhD and to work as a research fellow there for some time. And there I was working on things related to signal processing and actually wave propagation and porous materials, which is a subject that I've continued to work on since then, so sound absorbing materials and also sound field visualization, as well as wave propagation things generally. One of the things I'm actually very interested in is tires, believe it or not, wave propagation and sound radiation from tires. But in 1984, I joined the Ray W. Herrick Labs in the School of Mechanical Engineering at Purdue University, and have been there since, looking after a lot of grad students, and doing work for many industrial organizations. Let's say my longest partnership probably is with 3M, who I've been working with since about 1994 on things related to sound-absorbing materials. Originally, their product Thinsulate, but more recently, things like micro-perforated materials and other kinds of novel sound-absorbing treatments. And I think that probably brings us up to date anyway. So it will be interesting to meet you all and also try to address your concerns with respect to noise control. So make sure that you let us know what you're interested in, or if you have questions, you should feel free to ask.
Okay.
Thank you.
Thank you, Stuart. Well, I again thank Stuart to coming down to India, and then I will tell you my association with Professor Bolton is, when I was a postdoc fellow at Purdue, I was about 93, 94. He was in an office just across my office, and we used to meet at the Xerox machine having coffees, and that's how I know him. And then we have interacted with him professionally. My student, Dr. Fatima, spent a year with Stuart in his lab as a postdoctoral fellow, and then we have a common interest in natural materials and so on. And then, of course, those of you who have not been to Herrick Labs, that's a lab you must all see. It's the best of its type in the world, and they do everything on noise control there. Okay. With this, I would like to conclude this introduction session, unless you have any specific queries about the logistics, and please bear with whatever we have providing you with accommodation and arrangements, and we will fix some of those teething problems if there are any, and so on. And then I wish you a happy stay and a good learning experience at IIT Kharagpur. Thank you all. Wait for those guys, I guess. You all ready? Yeah. We'll go live now. Welcome everybody. We are starting the session on basics of vibration. Well, before I go into the basics of vibration, I will give a little background regarding what is this about. Basically, any oscillatory motion of a body about its equilibrium position would be a vibration. But if you look at a body, sometimes I can say that the center of mass moves in 3 independent directions, or also rotates about these independent directions of rectilinear motion, and there are rotations maybe theta x, theta y, theta z, and this is the center of mass. So here we are not saying anything about any other points in this body, okay, and this would essentially mean as a rigid body. So everything, any motion of this body is about this center of mass, and that is what is a rigid body. It does not undergo any elastic deformations, and that's an assumption which we are making for any body. But if you think at any structure, I can break it up into infinite such small bodies, and every infinite small body will have these independent motions and 6 degrees of freedom. So a degree of freedom is a independent direction in which I can describe the motion of the body. So a rigid body in space would thus have 6 degrees of freedom, where the points in the body do not deform, do not have any motion, but only it is defined by the motion of the center of gravity. So as opposed to another field is this elastic body, where every point could have motion. Okay. So it is up to, when you are talking about rigid body dynamics or elastic body dynamics, we can differentiate between how many degrees of freedom system. So today we will be focusing about the motion of these rigid bodies, and then when I say 1 degree of freedom, a rigid body is perhaps only allowed to either move in one direction x, either forward, positive or negative. So, and it is constrained physically not to move in the other 5 degrees of freedom. Okay, we can set certain constraints and then not allow it to move. So now we will talk about a body which will only move in 1 degree of freedom system. So this body, how do you characterize this body? By its mass m. Okay, and this is a single degree of freedom system. So this vibration has a lot of engineering applications. Vibrations are good, vibrations are bad. Okay, vibrations are good in one sense. I will give you an example. You have an ultrasonic jewelry cleaner. We use ultrasonic waves to clean our jewelry. We use vibrations as an indicator of the machine's health, and that's an area where I do some work on machinery condition monitoring, by understanding the vibrations out of the machine, understanding the frequency contained in that vibration, and then trying to find out what's wrong with the machine. Okay, we use vibration for transporting particles. We have vibration for transporting small particles, conveying, etc. But vibrations are harmful. Vibrations would induce fatigue stress in a material. Vibrations would induce discomfort to human beings. Okay, vibrations would produce noise, and that is why we need to understand what are the basics about this vibration. Okay. So I will not go into reading the slides. Okay, some of the slides, by the way, have been prepared by my students. And then, of course, why is many of the applications, like I just mentioned to you, through vibrations we can find out the dynamic behavior of the structure by measuring vibrations. We give a excitation to a body, some force, this body is going to respond. So, looking at the response by the force, I can find out the system properties, and that is something people which they do in the experimental model analysis, which you are going to see in the lab later on. But before we go into these experimental modal analysis, I am going to tell you certain few definitions and so on was related to a single degree of freedom system. Now, if you look at this body here, this is a rigid body of mass m supported by a spring of stiffness k and a damper c. And why is this a single degree freedom system? Because it is not allowed to move in any other direction but x. And if I apply a force to this mass, I would have a free body diagram, okay, and then I can write the equations of motion for this body, and then I will get, this is the equation of motion, mx double dot plus cx dot plus kx is equal to the external force. Solution to this second order differential equation is the response of the vibrating system, and I am sure playing around with the values of m, c and k, you will get the different parameters of this body. For example, natural frequency omega n, the circular natural frequency omega n is root over k by m, where f is equal to omega n by 2 pi, where omega n is in radians per second and fn is in hertz. Okay. In many of the industries, you will see sometimes they call it as CPM, cycles per minute, and then it's nothing but you have to divide it by 60, so you get cycles per second and so on. So just keep that in mind. Many times when people from the industry, they talk about so many CPMs of frequency. This is nothing but cycles per minute, so divided by 60 will be cycles per second, and it would be hertz and something to keep in mind. But because of the damping present in the system zeta, I get the damped circular natural frequency omega d as nothing but omega n times 1 minus zeta square. Okay. And this is the case where we have, if this force is not there and I perturb the system and left it to oscillate, because of damping it would cease to perpetually vibrate, and that would be nothing but as the free vibration response of a system. When the external force Ft is 0. But in many cases, you will see that there is an external force, and what are the sources of this external force on a system? Okay. I'll just give you an example. Maybe I have a machine on a shop floor supported on some sort of an isolators. Okay. And then I have some pressing operation happening, some hammering. So there is a force getting transmitted to the ground. So as you know, waves can transfer in solid. This force is going to come here. So in effect, this body could be affected by a ground force or a ground motion, and then this would have a problem, this would have a response. Now I'll give an example here. Imagine this was a laser machine where you are trying to measure displacement of the order of microns, okay, with a laser beam, or you are trying to focus a set of lens system like in a scaling electron microscope. What if ground vibration, there is some motion, some force coming to the body? It would give a response wherein the body itself would shake or vibrate, and you would have a tough time focusing your laser beams. So you will see in a lot of the industrial applications, there are vibration isolators in place to reduce the transmitted force, transmitted motion. We will see different cases. Imagine a ship deck where you have an anti-aircraft gun, you are firing the shells, the recoil motion needs to be absorbed, otherwise what is going to happen? The ship structure is going to get external vibration forces, and repeated vibration forces would lead to fatigue failure. So, ground vibrations in metro rail is a problem. Ground vibrations because you are in a test lab where you are doing sophisticated measurements, but you have a highway passing by, lorries and trucks with heavy loads are applying. So, all these motions are going to get transmitted. So, we as engineers have to do a good job in isolating these systems from external vibrations, external forces and so on. So, coming back, when we have a force, we have what is known as the force response of the system, and obviously if considering a harmonic excitation, anything which is a function of sine or cosine is a harmonic excitation. So, this is a harmonic force, and I am sure all of you would have solved this in your first year differential equation classes. What is the solution to this? It has a complementary function and the particular integral, and then the solution is a combination of these two xp and xc, and the roots of the equations would be you calculated, and then we will get the complementary function and so on, and then depending on the initial conditions you can find the solution and then you can plot them. But what is governing the amplitude? It is this damping ratio zeta. Okay. Sometimes you will see in vibration isolations at resonance, now of course you will see that at resonance, by playing around with zeta, this amplitudes could be coming down, could come down. Okay. So, we have to know where is this resonance and how by playing with damping I can reduce the amplitude of motion at resonance. So, in a free vibration system, for the undamped case, this is the solution to this, and I am sure those of you who are students, you can use MATLAB to plot these functions and play around with these values of zeta and see which is an undamped case, damped case, critical case and so on. Okay. So, for a body of mass m, stiffness 1000 Newton per meter, initial displacement of 0.02 meters, initial velocity 0 meters per second, the amplitude of motion of vibration as a function of time for different cases of damping is plotted here, and ideally we would like to have a damped case. We would not have to have oscillations going all the way. Okay. So, inherently in systems, in vibrating systems, there is material damping, we given external damping and so on, and then we can reduce the amplitude as given out here. Now, somebody may ask me, how do you quantify vibration? Okay, you showed me a plot of displacement versus time and so on. So, this xt is nothing but a sine omega t, where this is the time period and time period is nothing but 1 by f, and f is omega. So, this will become 2 pi by omega n. Okay. So, or omega or so at somebody asked me what is the amplitude of vibration, I would say A as in A units of displacement. A. So, what is the velocity of this motion? X dot t is nothing but d by dt of x t. This is A omega cosine omega t. So, the amplitude of velocity is nothing but a omega. Similarly, the amplitude of x double dot t is nothing but acceleration is minus, of course, if you take the amplitude a omega square. Okay. So, you see so this is displacement, this is acceleration, and this is velocity. So, vibration can be represented either as displacement or velocity or acceleration, but then sometimes you have to say again at what frequency omega or f and so on, and you know the relationship between omega and f. Omega is nothing but 2 pi f. Okay. So, I will pose you a problem. If the acceleration amplitude is 10 meters per second square at omega is equal to 1000 radians per second, what is x dot t and what is x t? Okay. It's very easy. All you have to do is divide 10 meters per second square by omega. So, 10 by 1000, and that would be the velocity. So, this becomes 10 millimeters per second, and this would become similarly 10 by 1000, 10 microns. Okay. Something to remember, it's easy to remember tens and tens. So, in fact, there are handheld vibration generators which generate 10 meters per second square at 1000 radians per second. So, that when you put a transducer in your velocity mode, that means that corresponds to a vibration of velocity of 10 millimeters per second at 1000 radians per second and 10 microns at 1000 radians per second. We will see that in the lab tomorrow. Okay. And of course, omega this of 1000 radians per second corresponds to I think somewhere around 159.2 hertz. Okay. So, vibrations can be represented either as velocity or as acceleration or as displacement as you need to report in. And I had told you about amplitude. I can find out the RMS vibrations, and that we will discuss later on when we talk about signal processing. So, coming back to the discussion on this force vibration. So, if my external force is f naught sin omega t in the non-dimensional form, okay, I will have this is how this vibration would change with frequency and damping, and this is known as the dynamic magnification factor. And if you plot this, this will come down vary with frequency ratios omega by omega n and also with zeta. And like I was telling you, this dynamic magnification factor would be very low if I increase the damping at resonance, but not at other frequencies. So, damping treatment is done to reduce vibrations at resonance of a structure. Of course, we have to find out the methods to find out resonance of that structure and where this resonance is occurring, which particles or which area they have large motion. And of course, if you look at this at resonance, what is going to happen to the phase angle? Okay, that is another way you can identify how phase angle will undergo a change of 90 degree. Okay, and this is what is the magnification factor. You will see how by increasing zeta this amplitude reduces. Frequency ratio is nothing but omega by omega n. Okay, and at low damping this changes by 90 degree. So, if you have a system where you can measure the response and the force simultaneously, and you can plot force in many of the analyzers, you can find out easily whether resonance has occurred or not. Otherwise, what happens many times the system would always vibrate at the forcing frequency. Okay. When naturally excited and left to oscillate, a system would oscillate at its natural frequencies. But if I am giving a forcing function, the system would operate at its forced frequencies. Okay. So, a good designer would never allow any system to operate at its natural frequency. The forcing frequencies should be away from the natural frequencies, otherwise I am always driving it to go under resonance and fall apart. And this particularly happens because I was telling you, every system, for a lab we are for this class we have discussed that every rigid body has a single degree of freedom system. Okay. But in real world it is not that. You talk about large turbines, okay, long shafts. There are many modes of vibration. There are many natural frequencies. Okay. And what if the you talk about a gas turbine in an aircraft? If a pilot is operating the gas turbine at its resonating speed, that would be disastrous. Okay. So designers tell them beforehand these are the safe regions wherein you can operate, and at resonance it takes time for the amplitude to build up. So quickly we need to move away from resonance when we are speeding up, be it a turbine, be it a paper mill, etc. Okay, so keep that in mind. So coming back to another aspect, when we have a system, so this could be a mechanical system. The response could be either a displacement as a function of frequency or velocity or acceleration, and there are certain names given to this transfer functions. Okay. Compliance is x by f, inverse of that would be the dynamic stiffness, mobility, mechanical impedance, accelerations, and dynamic mass. So sometimes we work with mechanical impedance and mobility. When you study about acoustics, you will see what are the different other forms of impedances, acoustical impedances, and so on. And then for any system, these transfer functions are something inherent to that system, and they carry information regarding their natural frequencies. Okay. But mind you, to find out about the system, I need to measure these two at the same time and simultaneously. Causality effect has to be maintained. I cannot excite a system today, come back tomorrow and measure and then try to find out its natural frequency. That does not work. Okay. And that is why you perhaps would have, those of you are coming from the industry and those of you have used, why we have a dual channel FFT analysis to begin with. Okay. A single channel FFT analysis would not do that. Okay. So simultaneously they need to be measured, and then we can find out the system's characteristics. And these are some of the functions which you can plot yourself for a spring, for a damper, for a mass, and then we can see how they are related with the phase lead and lag. And this is a Bode plot where we show the magnitude in decibels. This is different than the acoustical decibels, and then the phase is in degrees. Okay, magnitude phase plot, because this transfer function as a function of omega is a complex quantity. So in a Bode plot like shown here, I have magnitude and phase, or I could also have a real transfer function or FRF and an imaginary FRF, and that would be a Nyquist plot. And many of you who are familiar with controls, you will see the use of these kind of plots. So it is a way of representing a complex quantity, either magnitude phase or real imaginary. Okay. Sorry. Okay. A complex quantity can be represented this. Now I'll just briefly show you, just to excite you, that what is there in this modal analysis. Okay. So, if you will see here, this is a plate structure wherein we are giving in a force by an electromagnetic shaker, and there is a transducer here which is known as an impedance head, which will simultaneously measure the force and also the displacement. This is one form of excitation. Sometimes for quick testing we have an impact hammer wherein there is a force transducer here. So, when you strike a structure, it will simultaneously measure the force. Okay. And simultaneously at another point, if you can see here, there is an accelerometer which is measuring the vibration. So, we need to record that as well, and you can find out the transfer function and then find out the natural frequencies of that plate. This is a small system. If you have been to any auto industries, you will see vehicles instrumented with so many accelerometers all around them, and it could be instead of a single input single output system, we could have a MIMO system, multiple output, multiple input multiple output system, and so on. And another thing which you will see later on is what is known as whether this X which I have measured is because of the force or not. I can find out what is known as the coherence between the input and output. Like coefficient of correlation, if you recall in statistics, is one signal related to the another signal, or is it because of some extraneous noise. So, keeping a tab on coherence is a good thing when you are doing such dual channel measurements. So, if you look, that is what I am. So, this is the coherence, and then you will see the FRF of acceleration of this system, and you will see one frequency is at 993 hertz, another one is close to 1985 frequencies hertz. Okay. So, this is how natural frequencies of systems can be found out. Okay. But if the system is large, we can and of course, it depends on the boundary condition also. So, you can hang it from a ceiling to simulate simply supported conditions. You can lay them on a soft sponge to simulate to simply supported conditions. You can fix them to the wall to make them as a fixed end, free end, and so on. So, there are different scenarios depending on the testing you can do this test. Okay. This is of course, nowadays there are a lot of numerical techniques available to do experimental modal analysis, and this is a cantilever beam of 300 by 50 by 10 mm, wherein an harmonic excitation was given from 50 to 70 hertz, and the natural frequencies of the beams were found out as 92.5 hertz and 575 hertz. And you see at the phase plot there is a change of the phase angle at resonance. Okay. And these are indicators that a resonance has occurred. Now, we will with this kind of an understanding, we will see a few other issues of vibration isolation and transmissibility, and that is one of the reasons. If you recall, when in the first class I was talking about noise control and controlling the structure-borne energy flow. Structure-borne energy is coming through a structure. Structure could be a beam, structure could be a column, could be a plate. So, all that energy which is coming in need not get transmitted. If I stop the transmission, I would be stopping some of the structural energy coming into the system. I could do a vibration isolation, and I will give you another example of vibration isolation. For example, if you have seen a truck, and usually some of these trucks, they have, and there is an engine here, and then the engine is on a frame, and the vehicle components are put on a frame, and sometimes this cabin is actually all the way put on isolators. Even these engines are put on isolators. So, what is this isolator doing here? If you look at a vehicle here, this engine is generating some forces because of the gas forces and because of the inertia forces. I may have a balanced engine, despite that some forces would come to the structure of the vehicle or the chassis of the vehicle. We do a good job by isolating it, and further, if this cab was not isolated, what would happen? This entire cab would vibrate. If the cab vibrates, the air molecules would vibrate, and then finally everything is going to come to your ear. So a good isolation is to be done. Okay. So if you look at the machines are mounted on springs and dampers to minimize the transmission of forces to the foundation, vice versa, and I also sometimes do not want forces coming from outside to inside. Maybe you are in an office room, there is a press shop next to you with pressing operation going on. The forging hammer coming down, every time it comes down, a lot of force coming in. So that needs to be blocked. So we can design isolators. Okay. So if you look into this equation, the transmitted force is given by this expression here. Let me quickly move over to the next slide. The force transmissibility ratio is defined by this component. Okay, 1 plus 2 zeta r whole square, and everything under root, and in the denominator we have 1 minus r square plus 2 zeta r whole square root. So an interesting thing happens here at omega by omega n greater than 1 root 2, that is 1.414, you will see that the transmitted force is less than 1. Okay. So how do I ensure that the transmitted force, whatever is coming, less of it is getting transmitted? So that if I select my zeta or select my omega n of the isolator, omega n is nothing but k by m. M is of that body mass, k is the isolator stiffness. So I can go to the manufacturer's catalog and select an isolator with an appropriate k, so that when I plug it in this equation, I have a force transmissibility ratio where it is less than 1 or this omega n is greater than 1.414. Okay. So when you go to the market, you just don't buy any pad, any isolator and put it. It has to support the mass, plus it has to have characteristics so that the zeta, etc., so that the value of omega n which we measure or calculate is less than greater than root 2. Now another problem which will come is, what if the base is having a motion? What happens to this guy's response? Okay, many times base motion is there. So I can find out the expression for this is dependent on these again parameters. Okay, so this is the principle behind use of such base excitation for as if this base was vibrating and I wanted to measure the motion of this by having an sensing element at mass m. Okay, I could measure it relatively, I could measure it and find out what is the acceleration or the motion of the base, and that is the principle behind the development of accelerometers, where the sensing element could be piezoelectric, could be strain gauges and so on. This is a demonstration. Of course, I understand we are having some problems of this video here, but then you could have seen the motion of this isolation because of a base motion. Maybe in some of the later slides, once I can fix the slides, I will show it to you later on this demonstration. You could see the motion happening. This is a numerical example which I have borrowed from Einmann's book on engineering vibration. By the way, personally I recommend that's a good book. There are many other good books, but that's a good book which has a lot of the developments happening in the recent areas of signal processing, modal analysis, which has been put in engineering vibration. Okay, and I believe at IIT Kharagpur we use this as an undergraduate text in our courses as well. So basically, you have a vehicle which is moving on a wavy road. So we would like to see what is the displacement of the vehicle. Imagine you could be sitting in this car, okay, and this could be the effective stiffness and damping of your isolation system, and you are going on a wavy road. And I am sure all of you have experienced going on a wavy road at different speeds. Okay, maybe if you are going on a large bus or a small motorcycle, your experience is different because your mass m is different. Okay, and that's just to give you a feel of what this wavy road can do in terms of vibration. And imagine nowadays, we have a lot of this. In modern cars, we have this engine control unit. And then we have the, of course, nowadays, earlier we used to have, when the CDs came onto automobiles, we used to have the CDs skipping tracks when we are going on wavy roads. But those are things of the past. Today people work from streamed music out of flash drives or your iDrive systems. But then another component which we have is the ECU, engine ECU. There are chips. Imagine if the chips are exposed to high levels of vibration when you are going on wavy road. What if the single pin of that IC chip breaks? Your car or vehicle is kaput. Okay, you cannot go anywhere. So we, as designers of isolators, we have to be careful that the engine ECU control unit, the vehicle control unit, all these sophisticated electronics items do not fail because of excessive vibrations coming from the ground. You go on a wavy road and so on. Okay, this is just an example. So you will see if you change the speed or if you work out the numerical here, a 0.01 displacement boils down to a 0.003 meters displacement at the vehicle. And if you are increasing the speed, effect could, that's a homework you all could do. Change the mass, you will see the different effects and so on. Okay. Now, in terms of, if I just briefly recap what we have discussed so far: single degree of freedom system, free response, force transmissibility, vibration isolation, base excitation. Okay, but there are issues wherein I have made a system and then somehow I have a large motion at a frequency. Okay, vehicle has been made, component has been made, so I can design a system which is known as a tuned mass damper. If this is my primary mass, I could attach a secondary mass having the same natural frequency to this system, and then you will see I can shift these frequencies and lower down the amplitudes. Okay, my objective is to lower down the amplitude of motion, so I can have such tuned mass dampers as a fix in many systems. You would have heard of the Burj Khalifa. Okay, if the skyscrapers sway because of large wind motion, I can have tuned mass dampers, whether the tuned mass damper is vibrating and then the primary structure has less vibration. I will give you this example here. This is known as a tuned mass damper, and it is sometimes also known as a moose damper. The horns of a moose looks like that. So if you have seen the power lines, large power lines, transmission towers, and then okay, and imagine because of wind blowing, this cable has large motions. Okay, and then there are many cables. If because of this large motions, two cables come and touch each other, what kind of problem you guys are going to get into. Okay, so if you closely notice, next time you are traveling on a highway next to a power transmission line, you will see such tuned mass dampers attached at these ends. Okay, so one large, and they are tuned to few of the natural frequencies of this catenary, which is undergoing vibration, and we will demonstrate this to you in the laboratory. So these masses, there are 4 of these masses, they will only oscillate at a particular frequencies, and there are about 4 frequencies. Manufacturers say this kills most of the frequencies by which these cables vibrate. That is an example of a tuned mass damper. People have them in baseball bats so that you reduce the vibration and so on. And Incidentally, we have a lot of foundry industries in India, particularly in eastern India. They just cast these and export it worldwide. Okay, these are nothing but simple aluminum castings. Okay, the reason I have them in my lab is they gave me a few to test in our lab to see what the natural frequencies are. So I thought this is a good thing to demonstrate to the students about tuned mass damper. Okay. Wherein actually in this black table we give an excitation, and then you will see at different frequencies when you do a random sweep at different frequencies each one of them is going to vibrate. I have used this in, many times in reducing driveline vibrations. There is torsional vibration in a drive shaft of a vehicle. To reduce some of the driveline resonances, we have used tuned mass damper systems as well. So this is the equation behind the primary mass and the secondary mass, and then you can play around with these equations. So without mass damper, you see the amplitudes are very high, and then once I have the tuned mass damper, substantial reduction, and I would say that's a good engineering fix solutions to many vibration problems. Okay. I understand again there is some problem with this demonstration. Maybe if not here, we will demonstrate this to you in the lab when you come. Now another aspect is this rotational systems. See what happens in many systems, in many machineries we have shafts which are rotating. You talk about turbine, talk about a pump, talk about a motor, talk about a gearbox. There are shafts rotating at different speeds. So rotary motion is also a degree of freedom. So they will also have a resonance at a particular speed. So as again a designer, as giving an example of that aircraft, so pilots are instructed or they have safe limits not to go into that speed. They have in the control mechanism. Okay, same is true for even in a I'll give an interesting story. I was working for a small project with a paper mill. If you think of a paper mill, there are about hundreds of rolls, okay, and which rotate at different speeds, and each of these rolls this could be as long as 4 meters, and this diameter could be as big as 1 meter, and they are supported on bearings. Okay, and there will be series of rolls, all throughout the paper mill, and so on. And then they will go some like this, and so on, different processes, and some are heated, and so on, so that the paper finally which comes out, it's rolled here, and they go at certain linear speed. For example, the paper typically say 1000 mpm. In paper plants, they talk in terms of how many meters per minute. Okay, so I have just drawn here 4 or 5 rolls, sets of rolls, and the plant management wanted more production, so they wanted from 1000 mpm they wanted to go to 1200 mpm. Okay, increase the linear speed. That meant increasing the speed of these rolls. Okay, they tried that without any engineering, and there are failures. Okay, and then they asked us to look into it. We calculated the individual critical speeds of these rolls. So there are some speeds at which these rolls would be under resonance. So imagine again, repeated resonance means you are under a lot of fatigue stress, and then eventual failure. So critical speed is that way very, very important. I cannot arbitrarily increase the speed. Okay, if people, those who would have done experiments in the lab, you would have seen how again the stiffness of the supports play a role in damping the amplitudes of the motion of this shaft. You would have heard of squeeze film dampers in the bearings, fluid bearings. Fluid bearings, a lot of dynamics could happen by playing with the stiffness of the fluid in the bearings, which support the rotors or the rolls. And just to give you some insight in machinery noise, we will see these bearings are problematic in terms of vibration, in terms of noise. Okay, so we will see that later on. But large machines, because of the heavy PA load, we have to have journal bearings, and small machines we can have anti-friction bearings, etc. So, but again, imagine on top of it, if there was an amount of unbalance, so every rotation there will be an unbalanced force occurring, and that would give rise to more loads on the bearings. So, bearings would again prematurely fail. Okay. So, critical speed is thus important that we have the unbalances under control. And then another example is your tire. Okay. Other day I changed the tire of my wife's car, so I realized how important balancing is. Okay. If you do not have even if a new tire, you do not have put a balancing wheel, balance it, every rotation you are going to get a impulse force. And if you go to the motor companies, they make artificial unbalances and then input that as a force to the tires, and then see from a transfer path analysis what is the noise level because of such impulse inputs into the tire and then at the passenger ear location. So, these are studies people do. Okay. So, we as designers, we should know the critical speeds of any rotating shafts, similar to what we have talked about in linear vibrations. And for large rotors, you can do what is known as this study of this estimation of this rotating speeds by finite element models. Okay. And then this Campbell diagram is there. You can find out the rotational speed and the natural frequencies of different modes, because I cannot treat a rotor as a single degree freedom system. There are many modes. Okay. So, one has to be careful about the modes and the operating speeds, and the safe zones would appear on your Campbell diagrams. Okay. So, this kind of studies is done. Okay. So, to summarize whatever we have discussed in the vibrations, we have talked about single degree, of course, rigid body, elastic body, and then we have not discussed anything on elastic body. And then we will see when you talk about flexural waves in elastic body, how the wave speed matters, how the medium properties play a role in the propagation speed of the wave. But coming back to the rigid body of the vibration of this system, forced response, free response, base excitation, forced transmissibility, tuned mass damper, critical speed. Okay. And I would close with a little discussion on damping. Okay. There are many forms of damping, viscous damping, proportional damping. One is an hysteric damping. Some say we can have the viscous damping where the damping force is proportional to the speed. Okay. And then some of these values you can find in handbook for different materials. Some you can find out by measurement, the going up a curve, going up a loading curve, coming down, you can find out the hysteric damping and so on. Okay. So, in terms of this kind of a background, if I would say that if you looked into any undergraduate book on vibration, Thomson, Seymour Sinkel, Inman, okay, you would get some insight into the issues in vibration. And personally, I feel, I just was talking to another colleague of mine from US. We met in a conference last week. In fact, I asked him the same question, what do you say about teaching vibration to undergraduates? And it seems the ASEE did some survey, and a feedback they got is, if 90% of them want that if everybody has understood the single degree of freedom system, you can manage the situation. But of course, I have my colleagues in the department, experts in nonlinear vibration and going to chaos and all that stuff. We can do this more detailed analysis of vibration as well. But from an acoustical point of view, I think this should let us survive a course on acoustics and industrial noise control. And I'm sure if there's anything else, Professor Bolton is going to fill us in on that. Okay. Thank you very much.